All right, we've got this little block that's going to go down this track through the loop to point C, where it's going to be launched from the track. And in part A of this question, we just want to calculate the speed of the block when it leaves the track at point C. And you are told that the track has negligible friction. So we can use conservation of mechanical energy, K initial plus U initial equals K final plus U final. And the block starts from rest. So K initial is going to be 0. And that's the only term that's going to be 0. So let's just plug in the formulas. mgh initial is equal to 1/2 mv final squared plus mgh final. We have a mass in every term, so I can get those canceled out. And then the v final is the thing we're solving for. So I'm going to subtract gh final from both sides. So I have gh initial minus gh final, factor out the g, and then multiply both sides of the equation by 2, square root both sides of the equation. So vf is equal to the square root of 2g times hi minus hf. Plugging in all these numbers, it's going to be 2 times 10 times h initial is 2.0 meters. H final is 0.50 meters. And plugging all that stuff in will give you the answer of about 5.5 meters per second. Part B, explain why it's not possible to calculate the maximum height reached by the block after leaving the track at point C with the information given. So when the block gets to this point, and it's going to keep following this path to a highest point and go down here, why can we not figure out anything about the block at that highest point? And the reason is because we know the velocity of the block at this point right here, but we don't know the velocity of the block at this point up here, because that all depends on what the angle of the block is, with what angle the block left the ramp. We'd have to know this angle theta to know something about the velocity of the highest point. So at that highest point, we don't know the velocity or the height, and that's two unknown variables, but we only have the one equation, which is conservation of energy. We couldn't solve for both H final and V final at that point. In part C, describe what happens to the total mechanical energy of each of the following systems as the block moves from point A at the beginning to point C at the end. The first system is the one containing the block and the Earth, which is a fully closed system for this because we are only dealing with kinetic and gravitational energies. So because that system is closed and there's no non-conservative forces doing work on the system, the mechanical energy will be conserved. So we can say for part 1, the total mechanical energy remains constant. And then for part 2, the system containing just the block, well, now we're treating the Earth as providing an external force of gravity on the block. And the external force of gravity will either increase the speed of the block when it's going downhill or decrease the speed of the block when it's going uphill. So the kinetic energy of the block, if you're looking at just the block only, is going to increase until it gets to the bottom of this loop. Then it's going to decrease as it's going through the loop to point B. Then it's going to increase again as it's going through the other half of the loop. And then it's going to decrease as it's going up this hill. So that would be your answer to part C. The kinetic energy or the mechanical energy increases, then decreases, then increases, then decreases. Okay, on the dot, we want to draw the forces that act on the block when it is at the top of the loop at point B. So it's going to have a gravitational force going straight down, and it is also going to have a normal force going straight down since the track is above it. And those are the only two forces acting on the block. In part E, we want to calculate the minimum speed the block can have while still maintaining contact with the track. So we're going to do this by setting up Newton's second law for circular motion when the block is at the top of the track. Net force in the y direction is equal to mass times centripetal acceleration. And in this case, the net force in the y direction, if we treat the downward direction as positive, is going to be both the gravitational force and the normal force. So Fg plus Fn is equal to MAC, but to get the minimum speed that the block can have while still maintaining contact with the track, to just barely maintain contact with the track, that's where we set the normal force equal to 0. So with a normal force set equal to 0, let's plug in the remaining formulas. Fg is equal to m times g, and this is equal to m times the centripetal acceleration, which is v squared over r. We can then go through and cancel the m on both sides of this equation and solve this equation for v. So multiply both sides by r and take the square root of both sides. The square root of r times g is going to be, the radius of the track was given as 0.6 meters, and g is 10. This gives an answer of 2.45 meters per second. And so knowing that the block has to have that speed at the top of the loop, we want to calculate the minimum height where the block could be released from rest to still go around the loop without losing contact with the track. So right now we know the block was released from a height of 2 meters in the diagram. So we just want to know how much lower can we go? Like, where can we release this block so that it will still make it through the loop? So we're just going to set up conservation of energy with K initial plus U initial is equal to K final plus U final. The block is still going to be released from rest. So we'll go ahead and say that the initial kinetic energy is 0, and nothing else in here will equal 0 because we need to release it from some height. It's going to be moving at the top of the loop, and it has height at the top of the loop. So let's plug in the formulas. We have mgh initial is equal to 1/2 mv final squared plus mgh final. We can cancel out the m's in every term. And in this case, we are going to be solving for that initial height, the hi. We want to know how high we can release the block from. So we're just going to leave this equation as it is, but divide both sides by g. So if we divide everything by g, that will give you h initial is equal to v final squared over 2g plus gh final over g, which is just h final. And we can plug everything in now. The v final we just solved for was 2.45. So that is squared divided by 2 times g is 10 plus h final, which is the height of the top of the loop. And since the loop has a radius of 0.60 meters, the diameter of this loop is going to be 1.2 meters, which is the height at that point. So plus 1.2. And all of this will equal, if you plug in just this part right here, you get about 0.3 meters. So 0.3 plus 1.2, you get about 1.5 meters. And then part G, explain what would happen to the block if the block was released from a height slightly below what was calculated in part F. Well, we know in part F, this was the minimum height where the block could be released to still maintain contact with the track. So if you go to a height slightly below that, then the block would not have enough speed to make it around the loop, and it would lose contact with the track before even making it up to that height point.